In Calculus 1, we learned an integration technique called substitution. We have something like that in differential equations. So in this lesson, I want to give you some ideas for coming up with the creative substitution. But you'll handle the substitution much like we did back in Calculus 1. Now, if these steps look familiar, it's because, again, we did this in Calculus 1. It's just a little more involved in differential equations. Now, to get us going, I will choose the substitution. And again, just observe and get to where you can choose a proper substitution. Just like back in Calculus 1, there's no guarantee that the substitution I choose is actually going to work. However, let's choose for this one the substitution u equals x plus y. So you can kind of see my guidance in choosing that is because we've got an x plus y here that's squared. If that had been just a u squared, then perhaps I could figure it out. So let's see, where do we go once we decide on our substitution? Well, step 2, as I outlined it, was to do the derivative with respect to x. Now, we're going to just rewrite our substitution, u equals x plus y, so that y is equal to u minus x, and then do the derivative. Now, the derivative of y is the derivative of y. So when we say do the derivative of y is the derivative of y, dy dx. Now the derivative of u is the derivative of u. The derivative of x with respect to x is a 1. So here's our derivative. And then we make the substitution. From the original equation, do you see that here where we've got dy dx, we're going to put du over dx minus 1. Here where we've got y, x plus y, we're going to put a u. So let's change that and see what it looks like. Now that I see that, I see I can move the 1 to the other side, and this is separable. So we can get all the u's on the left, all the x's on the right, and do the integral. The integral of 1 over u squared plus 1 is the arctan of u. The integral of 1 is x, and then we'll put our constant over on the right. We'll solve for u by doing the tan of both sides. And then step 4 is to reverse the substitution. So in place of the u, we want to go back to our original and unsubstitute. So we'll put an x plus y in place of the u. And then hopefully we can finish recovering our function. So we'll try to solve that for y, which in this case is pretty easy. Just subtract x. And so there's our process for substitution in differential equations. Now let's try that with this problem. Now again, what I will do is I'll simply choose u to be the entire denominator. Solve that for y, do its derivative, and then substitute. In place of the dy dx, we'll put the 1/2 minus 1/4 du dx. In place of the 2x minus 4y plus 7, we'll put a u, and then see can we solve that. Well, if we multiply through by 4, and rearrange terms, we we see that we have something that's separable. Also, we can recognize that u equals 2 is a constant solution. We'll separate it and do the integral of both sides. Now, I'm not going to go through this by hand. The integral of u over u minus 2, you can do that various ways. One way, as you can see here, is to use your TI-89 and come up with 2 ln of u minus 2 plus u equals 2x plus c. We want to reverse the substitution. So in place of the u, we want to put 2x minus 4y plus 7. And of course, our goal would be to solve for the y to recover our function. The issue we have is, here's our y tied up inside the ln, and here's our y, which is part of this polynomial. In other words, there's no way you're going to solve for y in this expression. So we cannot come up with the function, but we do have here the explicit expression, and that's about the best we can do. So we recognize that the expression that we came up with is one possible solution, but remember, we also decided u equals 2 was a constant solution. Well, that doesn't tell us much in terms of our x's and y's, so again, we want to make our substitution. We would get the line given by this equation, which we can put in slope-intercept form. So we have that constant solution, which in this case is a diagonal line, and we have this implicit solution. Now I want to show you how this substitution plays out first off. So if we had something that looked like this, the obvious choice for u would be the y over x. And so that's kind of the idea behind what I'm about to show you. However, many times we can't recognize that because it's not exactly written like this. So sometimes we're just going to have to try it and see if it works out. So anyway, here's the idea though. If y is equal to x times u, then we do the derivative by the product rule. The derivative of x is 1 times the u plus x times the derivative of u. So dy dx would be u plus x times du dx. And then we would finish it out like we did before. Now, like I say, if you do this often enough, you'll learn to recognize some of these. However, this is simply saying when you see something of this nature, rather than doing all the algebra to try to get it to look like something that has a y over x in parentheses, maybe with some exponents sometimes, then we might learn to just recognize, hey, if we do the substitution u equals y over x, this will work out. Let me show you for this one. Now again, the substitution u equals y over x would be the same as y equals x times u, or dy dx equals, by the product rule, u plus x du dx. So let's substitute all of this and see what we end up with. Well, we'll do a little solving first. So here I've divided both sides by xy squared, and then we're going to substitute. Here's the dy dx from right here, and here is the y from right here. So we do those substitutions, perform some of the algebra, and then try to solve. Well, let's finish with some algebra. And notice that we have a separable equation. Now again, I don't want to seem too despondent on this, but there's a good chance that if you're trying a substitution, you'll get down to this point and you won't have something that's separable. So again, a little practice, a little recognition, and you'll learn when is this substitution going to work, and maybe you won't have to go through all this work and get to a spot where you just chunk it and start all over. Let me show you about this. Notice how we had a y cubed, we had an x cubed, and in here you've got a combination of x's and y's whose exponents come out to cubed. And the substitution worked out fine. Now again, to finish out the substitution, we simply move the u squared over to the left, the dx over to the right, and then integrate both sides. When we integrate both sides and solve for u, the last step is to unsubstitute. So we want to change the u back into y over x, and then see can we solve for the y. In this case, we can. Multiply both sides by x. And so that's what we were searching for, the function y. Now, as you can see here, this is talking about the format of Bernoulli equations. And notice what we have here is a y raised to some power. This looks a lot like our linear first order equations, but notice this is not just an f of x, it's f of x times y raised to some constant power. Now, the idea is just to recognize here's the substitution that will turn this into something that we can then integrate. So here's how that works with an example. Notice here we've got a y to the negative 3 tacked on to the end of our function, okay, and that's what we're talking about here. So we're going to choose the substitution for this one of y to the 1 minus negative 3. That's what our substitution guide says to use. So, just on faith, until we have done several of these, we'll just choose the substitution u equals y to the 4 and finish it out. Do the derivative and plug everything in, and then do the calculations. Now here, to finish it out, we need to multiply through by 4. So we don't have a 1/4. We need to multiply through by u to the 3/4. Turn that into a 1. And hopefully we can recognize now what's going on. Do you see that we have du dx, kind of like earlier in a previous chapter we had dy dx. We've got 12 times u, kind of like we had something times y, and then we had our function of x. This is a linear first order differential equation. We solved that by finding the integrating factor and then putting it into the format of mu times y, in this case u, and the integral of mu times f and again we try to solve for the u, which in this case is pretty easy. Divide through by e to the 12x. And then unsubstitute and try to solve. Well, Can't exactly solve it, but we can do the fourth root if we put a plus and minus on there. That's the best we can do at recovering our function y on this one.